Okay, so the first thing we need to do before we consider the loadings, you'll see it says, let's find there it is, determine the maximum negative moment at point A. And you see point A is this reaction. So I've got to find the moment at A as my uniform load moves around. Now you'll notice that with a fixed connection here and kind of a roller support here, that's four unknowns. I'm going to have to break this up into two pieces to find my reaction. Okay? So it's going to take us a minute just to draw the influence line for the moment at A. So let's look at the first case. So I'm going to first draw a free body diagram for AB. Let's see what that looks like. So at A, there's my moment. And we don't really care, but there's the shear at A. And then at B, that's a pin, so I'll just have a shear force at B. Of course, equal and opposite on the other free body. This would be the free body diagram from B to C. Well, since I've assumed my shear force is down here, it has to be up here. And then I get all the way to my reaction at C. That's what I've assumed. Okay? So, we've got two cases to look at. We've got to worry about the unit load operating here, right? And then the unit load moving over past B and going here. Even though I'm finding the reaction at A, you can see that if I put the unit load in this position here, I don't know the shear at B yet. Right? And then when the unit load passes over here, I don't know the shear. So we're going to look at these two free bodies for my unit load, and in both cases I'll get my reaction at B. So let's look at the first one when the unit load is between 0 and 5. So that would be the case where it's here, right? So, if I don't have any load on BC, what's my shear at B? 0. Everybody see that? So if I redraw my free body diagram at A, what I have is my unit load operating somewhere between 0 and 5. I've got my moment that I'm interested in, the moment at A. I've got my shear, possibly. But what's the shear at B? Well, if there's no load on BC, then BC is 0. And you can see that just by summing moments at C. If you sum moments at C, what does shear at B have to be with no load? Got to be 0. So that's it. That's what it looks like right there. There is no shear at B. The shear at B is 0. So all I have to do to find my moment at A is do what? I just need to sum moments at A, right? I don't care about the shear because the shear passes through A. It won't create any moment. So I'll have my moment, with my sign convention is negative. And then I'll have the moment due to the unit load 1, which is also negative, at a moment arm of X. So it looks like the moment at A is equal to negative X. And that's good from 0 to 5. Now what about the situation from 5 to 15? Well, now my unit load is over here somewhere. So that means my shear at B will not be 0. So I got to find the shear at B first. So in that case, I'm going to start with my free body diagram at BC. And it will look like this. it's 10 meters. I forgot to write up here that this was 5 and this was 10. So there's my shear at B. Here's my unit load. Now, it's measured from way over there is some distance x, right? This is 5 to 10, 5 to 15. And then I've got my shear at C, I assume. So I want to find the shear at B. How do I find the shear at B? I'm going to sum moments about C. So if you sum moments about C, what do you get? Well, this 1 is creating positive moment about C. But what's the moment arm right here? 15 minus x. So I get 1 times 15 minus x. That's the moment for that. And then I have this guy, which is the shear at B, creating negative moment at a distance of 10 meters. So it looks like the shear at B is going to be what? It looks like 15 minus x over 10. So now that I know the shear at B, I can go back to my free body diagram for AB, which now looks like this. I've got the shear at B, which I drew down, and it has the value of 15 minus x over 10. This is 5 meters. And then I have the moment at A. I'll go ahead and draw the shear at A, but I don't care about the shear at B, A, so I'm not going to worry about it. Again, I'm just trying to find the moment at A, so what do? I'm going to sum moments at A, just like we did up here. So I'll sum moments at A. That means the shear at A doesn't create any moment, so that moment is still negative. This is also negative. The force is 15 minus x over 10, and the distance is 5 meters. So it looks like the moment at A is negative, whatever all that is. So that 5 makes this just a 2, right? So that would be negative 15 minus x over 2. Do that right? Oh, something doesn't look right. What did I do wrong?
No, I think that's right.
Yep. Yep. All right, so let's plot it. So x, moment at A, I got to worry about 5 and then 15. So remember, I'm going to have a different equation from 0 to 5 and another one from 5 to 15. So from 0 to 5, it's this. So you plot this. At x equals 0, I get 0. At x equals 5, I get negative 5. And it's linear. Now from 5 to 15, I plot this equation down here. If you put in 5, what do you get? You get negative 5. It matches. You put in 15, what do you get? 0. So there's your equation, or there's your influence line for the moment at A. And this will have the units of meters. right? Because we're still multiplying everything by meters. Okay? So now what do we do? Now we actually solve the problem. The problem says I now have a 1.5 kilonewton meter dead load and a single load of 10 kilonewtons. So let me draw a little box here to kind of put that off. So for the concentrated live load, it has a value of what? 10 kilonewtons. Where would I put my single 10 kilonewton live force to create the maximum moment at A? Well, you take the maximum value, and it'd be right here at B. And it have a value of minus 5 meters. So the moment at A for that would be my 10 kilonewton live load times the maximum ordinate value, which is minus 5 meters. And I would get negative 50 kilonewton meters. So there's the moment at A due to that single live load moving around, but the best place for it to be to create the maximum moment is right here at B. Now what about the dead load, the uniform load? We might remember that we just talked about how to handle a uniform load. And how do we do it? We took the intensity of the load, which in this case is 1.5 kilonewton meters, and we multiplied it by the area under the influence line. So in that case, the additional moment would be the 1.5 kilonewton per meter times the area under this curve. It's a triangle, so it'll be 1/2 the base, which is 15 meters, times the height, which is minus 5 meters. I don't know what that's going to be. Somebody help me with that. Negative 56.25. And you can see your units are going to be kilonewton meters. So the total moment at A, you just add these two together. So it'll be negative 106.25 kilonewton meters. That's the maximum moment at A created by these two loading scenarios. That's a very testable problem. Okay? All right.